Hey guys, it's good to see you after break. Obviously, I'm not there, unfortunately. I'm going to be gone for a little while longer. I know that might upset some of you, and trust me, I wish I could be back as well. I hope you guys had an amazing break. I know that I had a great break with my family and just sleeping in, getting refreshed, enjoying Christmas and New Year's. So I hope you guys had the same thing. I hope you guys feel refreshed, slept in a lot, got to play with family and hang out with friends. And so I hope your breaks were great. Um, it's back to the grind, back to getting into things. We are starting some new stuff, so bear with me. But this is going to be stuff that we haven't talked about before. I wish I could be there to teach it to you in person, but we're going to make the best of it. Okay. So, in this, you are going to do some guided notes, something that we did before break. I made you guys videos before break, and it seemed that those worked out relatively okay. Now, I do have a couple of rules this time around. Please get your work done. Okay. These are very easy. All you have to do is listen. All you have to do is watch the videos and fill out as you go. If you miss one, that's okay. Rewind the video, go back. They're going to be on YouTube. Take the video back a little bit, find what it says, look at the slides. Your notes and slides are going to be the exact same. We will have some time to pause for some questions that I have in there because since this is new material, I want you to think about it. Some of the stuff that we do in school when we're there is you guys get questions to think about. So, same thing. All right. So, we are going to do some new stuff and I'm going to get right into it. But I hope you guys are doing well. I miss you all. And, um, you know, we'll get into it. All right. Let's go. All right. So, for your warm up today, you're going to do Earth's surfaces. All right. So, what we're going to start talking about is Alfred Wegener. Okay, it's Wegener, not Wegener, Wegener. Okay, so he's a German man, German scientist. And if you look up on the board, the left of the ViewSonic at the front, there is an entire bulletin board on Alfred Wegener and the things that we are going to talk about today. Okay, so moving puzzle. All right, so we talked at the beginning of the year about thinking like a scientist. Okay, so go back to when we had the note cards. Okay, you had to fit yourself through a note card. Seems impossible, but it was. Okay, I showed you guys how to do it. So, thinking like a scientist, put that science cap on. Let's think like scientists. So, if continents used to be joined together, what clues would you look for in order to prove it? Now I'm going to make me a little bit smaller over here so you can see this full thing. All right, so Pangea. Pangea was an idea that all the continents were put together. We'll talk about that a little bit more here in a minute. But I want you to look at those two pictures. Pangea is a long time ago, everything's put together. And these are our continents today. So you have South America, North America, Africa, and Europe, right? Okay, so write two ideas in your notes that could be evidence that all these continents were in fact one continent at one point. Okay. So before we get into any of the evidence, before we talk about Alfred Wegener and Pangea and get into all the details, I want you guys to think about a few things, few ideas, clues that might be on there. Now, with your notes, you have write two ideas. Okay, so if continents used to be blank, blank, blank together. Okay, if you look at the very top, if continents used to be joined together. Okay, so that's your first one. What clues, is your second one, would you look for to prove it? Okay, science is all about proof. Okay, now we have theories, we have laws. Okay, we have things that we know that are true and things that we think are true, but that plays a little bit of a role into what we're looking at here. Okay, so we'll get into that in a minute. All right, so some possible clues, types: shape, fit, fossils, rock mountains, climate cues. Okay, so I'm going to give you, it says write 2 ideas in your notes. Now, these 2 ideas cannot be the same ones that are on here. Okay, I want you to think a little bit more about a little bit more. Okay, I want you to give me more. Okay, use your brain. Don't just copy what's on here. Use your brain and think of 2 ideas that might prove that these 2 things were joined together. Okay, now pause the video so that you can do this. All right, if you're taking it back up, then if you've hit play, then you're ready to move on to the next slide. All right, so our ideas today, okay, our I can statements explaining what Wegener proposed. This is our continental drift theory. Lists 3 pieces of evidence Wegener used. Okay, we're going to talk about all the evidence of Pangea and continental drift. Tell the difference between a scientific theory and a scientific law. We have talked about that a little bit in the past. We will get into that as well. Describe how ocean floor maps help prove plate tectonics. Okay, so because of our ocean floor, we can prove plate tectonics, and we're going to talk about the lady that helped us do that. All right, our key vocabulary here. Now, we are only going to explain these, so you're not going to be able to fill these out now. In your notes, it has a place for definitions, but we don't know them now, and I'm not going to explain them now. So you're going to have to go back and fill those out when we talk about each one. Okay. So you have continental drift, Pangea, plate, boundary, mid-ocean ridge, trench, seafloor spreading, and subduction. Now, our fun fact for the day is that tectonic plates move about 1 to 10 centimeters per year. Okay, so our plate tectonics, although very big and powerful, move about the same speed as your fingernails grow. It's pretty crazy. Okay. All right. So Alfred Wegener. Okay. So 1912, that's when he was born. Okay. So long ago, the continents were joined together. This is the things that he came up with. This is what is our continental drift theory. I'm going to switch it up here so you can read it all. All right. So he thought that the continents were once joined. Okay, so that would mean North America, where we live, South America, Africa, Europe, Asia, Antarctica, all of the continents were one big, giant continent. Okay, so the first thing that he thought about is that they looked as though they were joined together. Now, we'll get into the whole puzzle piece explanation here in a minute, but he thought that they looked like puzzle pieces. So that is what he went off of to think about, hey, those things might go together. So these could have been joined at one point. Okay, so scientific thinking. All right, so he thought, again, long ago, the continents were joined. They eventually moved apart, and he called this idea continental drift. Now, it doesn't say so in here, but this is continental drift theory. At this point, it was just a theory. Okay. We didn't have the ability to prove it to be correct yet. Okay. So, this supercontinent that he's talking about is called Pangea. Okay. Which means all Earth. Okay. Now, Wegener's question down there says, why do so many cues match across oceans? Okay. We'll talk about that in just a second. Okay, there are four major ways, major reasons why Alfred Wegener had this idea that things were connected. Okay, now these were continental fit. Okay, so the first one that's on your notes is continental fit. Okay, so some coastlines look like they match up. Now, for instance, South America and Africa. Okay, so you have a little cutout. I will try and put a picture up here, but I think I might have one in a slide. So we'll talk. We'll make sure I show you that. But South America and Africa look like puzzle pieces. Okay, that rounded part of Africa looks like it would fit into the rounded part of the United States. So just by looking at the continents, Alfred Wegener thought they look like puzzle pieces. They look like they would fit together. And that's what initially started his thought process of the continents once being joined together. Okay, the second part is fossils. Okay, some fossils found on continents now separated by oceans. So let's say that you have a specific bird or a specific animal, any animal. Okay, if you found fossils of those in Africa and then also found fossils of those in South America, well, how did they once live on both continents? They obviously can't travel across the giant ocean, the Atlantic Ocean. So, how did they get from one continent to the next? So, that's one way that he thought that, well, if they were connected and eventually split apart, then animals of the same species would have been on that whole area. And when they separated, some were on one continent and some were on the other continent. Okay. And this is the same way with plants. Okay. So plants and animals, they can't swim across that ocean. They can't swim that far. So those fossils had to have gotten there somewhere, somehow. So that's how he came up with the fact that it was connected and once and then split apart. Rocks and mountain ranges. Now, when he started looking at the continental fits of how these things fit together, how South America and Africa fit together, and North America and Africa and South America all fit together. But he also started looking at the mountain ranges. Now, when he fit those things together, those mountain ranges started to line up as well. So, if a mountain range from one continent matches up with the fit of a mountain range on another continent, it would be logical to say that at one point those were one mountain range. Okay. And climate cues. So glacial scratches in places where things are warm today. So when glaciers were on the Earth, okay, before they all melted and went away, glaciers, when they go across the ground, leave scratches in the dirt and in the underlying rocks. So when you have these scrapes on certain rock beds, if those scrapes are in places where are close to the equator, like Africa or in the rainforest, and you can see those same scratches, then you would determine that at one point that continent was in a place that had the climate that could support a glacier. Now, you can't have glaciers in Africa right now because it would be too hot. They would melt instantly. Okay. When stuff gets temperatures around there get into 110, 120 degrees, depending, and humidity is ridiculous, there's no way that a giant ice ball would be able to survive an hour, let alone be able to travel through that whole area and scratch up the dirt. So you have to understand, or have to have the understanding, that at one point that continent was in a different place on the earth. Okay. But whew, but we had a big problem here. So Wegener couldn't explain everything. All right, so he had a believable mechanism, but scientists at the time thought continents were too big to move. The ocean floor was fixed and unchanging. Continents plowing through rocks didn't make sense. So when Wegener came up with this idea, he was not greeted with, "Hey, you're right." Um, much like a lot of scientists, nothing of Wegener's was even believed to be true until after Wegener died. So, in science, evidence matters, and the explanation has to work. So, he was missing a lot of things that Wegener couldn't prove. He didn't have the ability to do that in his current time period. So, Wegener actually died without any scientists actually believing in what he was saying. So there was a big problem with people believing what he was talking about. All right, so getting into a law and a theory. Okay, now we've talked about this a little bit. We're going to talk about it a little bit more. So, laws. This is describing what happens. Okay, so often with math. So, examples of this would be the law of gravity, the law of conservation of mass, the law of conservation of energy, Newton's three laws of motion. Okay, all of those would classify as laws because we know them to be true. This is describing what is happening. Theories are how and why. Okay, so this is a theory. So, theory is not a guess, it's supported by lots of evidence, but we can't say that it is 100% accurate. So take the theory of evolution or the theory of um, continental drift or other theories similar to those. We think theory of the Big Bang. We think that those things happened because we do have evidence that says it did. But we don't know for sure that this is what happens. Because if you remember from that video that we watched at the beginning of the year, theories can sometimes be discredited for a different theory that makes more sense. So, say continental drift theory, or the theory of evolution, or the Big Bang theory, or any of those, randomly we find more evidence and we conduct a different theory that discredits that theory. Okay. So theories can always be altered and can be different and can be made stronger or be disproved. Okay. So an example of that, theory of plate tectonics or theory continental drift theory, those things. All right, so some new evidence came from the ocean floor. This was in the mid 1900s. All right, so what we used to figure out that there were, let me explain it to you this way. How do you see the ocean floor? Now, if you guys remember when we talked about, actually, we haven't talked about it yet, but Mariana Trench is the deepest part in the ocean. Okay, so the Mariana Trench is the deepest part in the ocean. It is multiple Empire State Buildings into the Earth's surface. It is deep. Okay, there's even theories that the megalodon lives in the Mariana Trench because it's deep enough where it can hide. Don't know if that's true, but who knows? Okay, so up until the 1900s, we didn't know what was at the bottom of the ocean. We still don't know what's at the bottom of the ocean, really. 90% of the oceans have not been looked at. We have not even went into discovering or journeying through or finding evidence about the oceans. 90% of them have not been explored. Okay. So, how do we see the ocean floor? Scientists in this time use sound waves. Okay. A lot of us have heard of sonar. Bats use sonar. Okay. They have their screech or whatever, and however far it takes or however long it takes for that sound to bounce off of the walls and come back and they hear it, or however loudly they hear it, because I mean if it's further away it's going to come back, going to take longer to come back, and the sound isn't going to be as loud. Okay, so they use that to see where they are because bats are primarily blind. Okay, so they use sonar to get around. Scientists used the same theory to measure the depth of the ocean. What they got was a detailed map of the ocean floor. Okay, so they used sonar waves. Now, if you look at here, the little triangle that's up above, that's your boat. Okay, those triangles that are coming down, the light or the white, that is your sonar. Okay, and it's measuring how far it takes from the boat to get to the bottom of the ocean and then come back. Okay, so when they mapped the ocean floor, they found giant mountain chains under the ocean, deep trenches, and patterns that suggest that the seafloor was moving. Okay, now in the previous slide, okay, continents plowing through rock didn't make sense. The ocean floor was fixed and unchanging. Well, that was the big problem with Alfred Wegener's continental drift theory. But after they use sonar, they find giant mountain ranges, deep trenches, and patterns that suggest the oceans or the seafloor was moving. So, like I said, they didn't prove Alfred Wegener's continental drift theory to be correct until after he died. So, in the 1900s, when they decided to use sonar to map the ocean floor, they started to see evidence of what Wegener was talking about. All right, so Mary Tharp, probably one of the most important scientists to help us figure out what's going on with plate tectonics. Now, a lot of people don't know her, but I like to talk about her every year because I believe that she is one of the most important parts of this. All right, so in the 1950s, Mary Tharp used sonar depth data to draw detailed maps of the ocean floor. Now, in the 1900s, like we said, they started using sonar to try to see what was on the bottom of the floor. Mary Tharp used that data to create maps. Okay, so her maps showed huge underwater mountain chains, which later we classified as the mid-ocean ridge, a rift valley running down the middle, and deep trenches in other places. Okay, now this really helped us prove continental drift theory. Okay, these features help scientists accept that the seafloor and plates move. So Wegener came up with the idea based off of the fact that they fit together like puzzle pieces. And then Mary Tharp came along and she helped prove that theory to be correct. So, of course, you know, the he would come up with the idea and then she would just, you know, give us the evidence to make it correct, which is awesome. Okay, so what her maps revealed. I believe this is in your notes here. All right, so important ideas. Maps are well, where is that? All right, we're going to talk about mid-ocean ridges. Okay, so our mid-ocean ridges. This is a mid-ocean ridge right here. Okay, so on the left side, you have plate A. On the right side, you have plate B. Now, they're meeting in the middle. That's what's called a divergent boundary. We'll get into boundaries here in a minute, but I have about 5 minutes left of this video. Okay, so divergent boundaries. So this is new ocean crust forming at the ridge. Now, I can make a drawing on here, which I would love to when I would be teaching you guys face to face. I would make you a drawing to help you understand this. But this drawing works out just fine. This is under the ocean. Okay, so again, you have plate A on the left, you have plate B on the right. Now, these plates are moving away from each other. So if you see those arrows, that is the way that each plate is moving. Okay, so then you have magma. Magma from the Earth's core is moving up, or from the mantle is moving up um, through that mid-ocean ridge, okay, through the opening in the plates, and it eventually settles like that brown triangle above the magma. Okay, so it separates, and part of it goes one way, part of it goes the other way, and then it settles and it hardens. Okay. All right. So these are these key ideas. This is an underwater mountain chain. Okay, it's a divergent boundary, which means that they move away from each other. Your magma rises, it cools, new ocean crust is formed, and the sea floor spreads outward. Okay, this is the engine that drives plate movement. Okay, if we didn't have mid-ocean ridges, our plates would not move at all. Okay, there wouldn't be a way for them to move. This is the engine that drives plate movement. Okay. Now, ocean trenches. This is a different thing. So, in the first one, you have two oceanic plates. Plate A and plate B are both oceanic plates. On this one, you have an oceanic plate and a continental plate. So, think about the beach. Okay, when you're at the beach, there is an oceanic plate and a continental plate. Okay, so this little piece, you have the oceanic plate and the continental plate. Now the plates are moving towards each other. So instead of moving away from each other and the magma comes up, they are moving towards each other. So if you can imagine putting your hands up just like this, okay, now push together. One plate is going to subside, okay? All right, so you have one plate that it moves underneath it and one plate that moves on top of it. Okay, so this is called your subduction zone. Okay, so this little place down here where is underneath the plate is your subduction zone. Okay, the top part where you have both of them moving and one of them subducting over the other. Okay, you are going to have one that continues to move. Well, it's going to get a hump in here. So when you move these underneath each other, this one's still pushing up against it, so it's going to start collapsing on itself. Okay. What happens here? This is now a mountain. But this over here, in between these two plates, is our trench. Okay. So that constant movement forward towards each other is making those bend and break and eventually form mountains and deep ocean trenches. Okay. So deep valley in the ocean, convergent boundary. Convergent boundaries move towards each other. One plate sinks, subduction zone. Old crust is recycled. So under that subduction zone, this stuff down here is going to be melted back away, and it's not going to exist, and it's going to just go away. Okay. So that old crust is recycled.